Okay, we now start our lecture series on chapter 16, and chapter 16 covers the topic of traveling waves. So we're going to talk first about the theory concerning traveling waves, the equation governing traveling waves. We'll try to understand it in more detail, and then we'll do some examples about traveling waves. So the equation for a traveling wave, y as a function of x of t, is going to be a sine kx minus omega t plus phi. So we're going to try to understand the pieces of this and what each one means. This describes a transverse wave. A transverse wave is a wave that is propagating in the x direction, this way. Right? This is x and this is y. The wave is propagating in the x direction, but it's moving up and down perpendicular to the direction of motion. So the y, like this. So transverse waves, the wave propagates this way, but the actual object moves this way. The wave moves up and down this way, so it's perpendicular. Examples of transverse waves you can set up in strings, but just by simply moving the string up and down, right? An example of a transverse wave in nature is, for example, when an earthquake hits, the earthquake will send out two kinds of waves. One is known as primary wave. Primary wave travels faster. It's the first one that hits you. It's actually a longitudinal wave. Longitudinal. The longitudinal wave, the motion is in the x direction. It's propagating in the x direction, and it's also moving sideways parallel to the direction of motion. That's a longitudinal wave. The second wave that an earthquake sends, it's a little bit slower, is a secondary wave. Secondary wave, and this one is known as a transverse wave. So we call it PNS waves. The second wave that hits you when an earthquake happens, it goes a little bit slower, and it comes and it moves the buildings up and down. So the earthquake moves this way, and the building actually shakes up and down perpendicular to the direction of motion of the earthquake wave's energy. Okay, so that's the second one that hits you, and that's an example of a transverse wave in nature. Okay, electromagnetic waves are also transverse waves. Electromagnetic waves, transverse. Another example of a longitudinal wave in nature is sound waves. Sound waves. So that would be longitudinal, electromagnetic wave transverse. Secondary wave of an earthquake is transverse. So let's try to understand what this means. All this stuff inside of the sign have to have units of radians. So in this chapter, we're primarily going to be working with radians. So what do these mean? This one here means the phase angle, and it's measured in radians. So what's the purpose of the phase angle? The phase angle is essentially telling you what's happening to the wave at the beginning, when x is 0, when t is 0. So it's kind of like the initial conditions of the wave. So it describes the initial conditions. Initial conditions of the wave. So an easy phase angle, for example, would be 0. If the phase angle is 0 rads, what would that mean? Well, this would disappear. That means when x is 0, t is 0, y would be 0. You see? So x would be 0. When x is 0 and t is 0, that means y is 0. In other words, initially, the wave is actually right at the origin, right? And then I'll draw out actual waves a little bit later on and describe what they are. Okay, so that's describing the initial conditions. Kx has to also be in units of radians. X is the position, the horizontal position of the wave, right? And so K must have units of rads per meter, okay? And K is known, the official name for it is called the wave number or angular wave number, okay? So its units is rads per meter, and K is 2 pi over the wavelength. And later I'll show you that this actually makes sense. 2 pi stands for radians, and then the wavelength of the wave is the distance from peak to peak. This is meters, so rads per meter. So in terms of units, it works out. Okay, so K is known as the wave number. Okay, so now let's look at omega t. What does that mean? Okay, so omega t is describing the propagation of the wave as a function of time, right? And omega is known as angular frequency. Omega t must have units of radians. So omega must have units of rads per second. Well, we've actually seen this over and over when we talk about oscillations in physics 1, and we talk about rotation in physics 1, and omega keeps appearing again and again, and it always has the same units, rads per second, okay? So this is known as angular frequency. Omega is going to equal to 2 pi over the period of the wave. Well, actually, this is true for any oscillation motion. Omega equals 2 pi times the frequency, or 2 pi over the period, right? 2 pi f or 2 pi over the period. And would that satisfy the units it must have? This would be 2 pi rads, this would be seconds, so rads over second, so it would actually match the units it must have, okay? So let's draw a picture of a wave. Let's choose some easy numbers. So let's assume you have a wave that the phase angle is 0 rads. Let's assume K is 1, and the units for that would be radians per meter, right? Rads per meter. And then let's say omega is 1 rad per second. So let's draw this, what would happen to this wave, so we can understand. So how would we draw the wave? We would say y is its vertical position of the wave as a function of x. So let's draw different waves at different time intervals. In other words, different snapshots of the wave at different times. So at t equal to 0, what would this wave look like? So y would be equal to, its general function is y is equal to, since k is 1, you have x minus, and then omega is 1, t, and then the phase angle is 0, right? So you have y is a sine x minus t. A is simply the amplitude of the wave, which means how much up and down the wave goes, right? A wave that has a bigger amplitude is going to carry more energy, and we'll talk about the energy of waves later in a different lecture, okay? So right now, let's just assume the amplitude is 1, just for simplicity's sake. A is 1, so we can just say y is sine x minus t. So at t equals to 0, what's the snapshot of this wave going to look like? At t is 0. We can say y equals sine of x. So simply just draw a sine of x function. It goes like this. At 0, when x is 0, sine would be 0, right? And then you would have here pi over 2. When x is pi over 2 meters, right? The units here are meters, and the units here are meters. So when this is pi over 2 meters, this would be 1 meter, right? If we want to make this to scale, what would pi over 2 meters be? Pi over 2 meters, pi. So pi is 3.14 over 2, that would be 1.57 meters, right? So if I want to do this to scale, I should actually draw this bigger, right? So if the amplitude of the wave is 1, I write this as 1, and then therefore this is 1, this is 2, this is 3. So pi over 2 would be somewhere here, right? Pi over 2. Now I can erase my 1 and 2 and 3, and then just concentrate on the pi over 2. So at pi over 2, the wave would be here, right? And then at pi, right, when x is pi meters, what would that be? That would be 1, 2, 3, a little bit more than 3, right? This is pi. So the wave would go up and then come back down, right? So the wave at t equals to 0 looks like this, right? Then when we get to 3 pi over 2, so we take another of this, and then put it over here. So that would be 3 pi over 2. And then this is going to be -1. So then the wave looks like this, something like that, right? Like that. And then at finally 2 pi, which is going to take us to 6.28, right? So 1, 2, 3, 4. This is 5, 6, and then a little bit larger than 6. Right? So that would be pi right there. And then you go over here. So basically a simple sine function. And then you can draw the wave also here on the left side, and you can draw the wave over on the other side too. Just continue drawing. But we're drawing only one wavelength of the wave, right? So then what's going to happen? I want to know what happens to this wave as time progresses, right? So what's an easy time to choose? Well, since we're working with radians, a nice time to choose would be t is pi over 2 seconds. So what's this wave look like at t is pi over 2 seconds? At t is pi seconds, right? We could do t is 1 second, 2 seconds, 3 seconds, but it's going to be harder calculations, and we don't need harder calculations to do to visualize this wave. So I'd rather choose multiples of pi seconds, right? So what's this wave look like at t equals to pi over 2 seconds? What's this wave look like? Well, now you're going to have y is sine of x minus pi over 2. So when x equals to 0, what's going to happen? When x equals to 0, the way so sine of 0 minus pi over 2, right? So when x is 0, y is sine of negative pi over 2, so it's -1. So it looks like this, right? And then when x is pi over 2, then you got sine of 0, which is 0. So the wave looks like this, right? So basically the wave has shifted over, right? When x is pi, y is sine of pi minus pi over 2, right? Which is going to be sine of pi over 2, which is 1, right? So when x is pi, then you get 1 over here. So the wave looks like this, right? And then it's gonna, at 3 pi over 2, it's gonna be here. And then at pi, it's gonna be down here. And then if you add one more, that'll be 5 pi over 2, right? And it'll be, this was 2 pi, right? So this was pi, I should have written here 2 pi. And then if you move over another pi over 2, you will have 5 pi over 2. What has happened to this wave? This wave has moved to the right, right? This peak has gone over there, shifted, right? This one has gone over there, right? And another one from here came over, right? The piece that used to be here came over here. So everything has gone over. This one went over here, this one went over here. So by a certain distance, right? Let's do one more progression, one more snapshot of this wave, just to see what's gonna happen, right? So let's see at t equals to pi seconds, what's going to happen. Then you're going to have y is going to equal sine of x minus pi. So that means after 3.14 seconds, what's the wave look like? This one, after 1.57 seconds, what's the wave look like, right? So then what's going to happen? When x equals to 0, y is going to be sine of negative pi, right? Which is going to be what? 0. When x equals to pi over 2, y is going to be sine of negative pi over 2, because I'm putting here pi over 2 minus pi. So that's going to be -1. When x is pi, y is going to be sine of 0, which is 0. So what is that looking like? So different color so we can see here. It's going to go down, then it's going to go up, right? And then when x is 3 pi over 2, y is going to equal sine of 3 pi over 2 minus pi. That's going to be pi over 2, which is 1. Right? So then 3 pi over 2 is going to be 1. So the wave is going to go up. And then it's going to go back down. So what happened now? The wave moved over same amount of distance, right? This way. So this peak went from here to here. Then in another pi over 2 seconds, it went over here. And then same thing happened. This point went over here, then went over here. Right? This one went from this point that used to be here, went this way, and then went this way. So in other words, in equal time intervals, the snapshot of the wave is showing that the wave has progressed to the right. Okay? So what is the velocity of the wave? We can now measure that. Right? How much is the wave moving? Well, the velocity of the wave is the distance that it traveled during the time interval, right? So how much did this wave travel? It started at pi over 2 meters. It traveled pi to pi meters. So the distance here is pi over 2 in a time period of what? Pi over 2 seconds, right? From here to here, the snapshot was pi over 2 seconds. Then in another pi over 2 seconds, it traveled another pi over 2. So basically the distance it's traveling is pi over 2 over pi over 2. Pi over 2 meters over pi over 2 seconds. So the velocity of the wave is 1 meter per second. Well, so far, it seems like we can maybe generalize, but it's a little bit too early. Okay? Remember, what was the units of the k? The k was 2 pi over the wavelength, and the omega was 2 pi over the period, right? This one was rads per second. This one was, this one was rads per minute, and this one was rads per second. Well, simply by unit analysis, the velocity of the wave, we can argue, is some ratio of the two. So what should we do? V is equal to, should we do omega over k or k over omega? If we do omega over k, what are we going to get in terms of units? Rads per second over rads per meter. Is that going to give us the desired units? Okay. Let's see here. Rad's going to cancel. The meter is going to go up to the top. Meter over second. So it seems like if we want the units to work out, the velocity of the wave should be omega over k. Omega is its radial frequency, and then k is the wave number. So is it working out in our case? Well, in our case, so far, we only tried omega is 1, k is 1, right? Omega was 1, k was 1. So the velocity of the wave, just by simply the ratio, should be 1 meter per second. And from our analysis of the snapshot, it did come out to be 1 meter per second, so it's working out. The other thing we can try to see if this makes sense or not is this making sense? K is 2 pi over lambda. Therefore, the wavelength of the wave should be what? 2 pi over k, right? Wavelength is 2 pi over k. In our case, what was the k that we tried? The k that we tried was 1 radian per meter, right? So what's our omega? Let's see, lambda is 2 pi over k, 2 pi, right? In other words, for my wave here, for the value of k being 1, I should get the wavelength of the wave is 2 pi meters. 2 pi meters. Is it 2 pi meters? It certainly is. It goes up, it goes down, it goes up. It repeats every 2 pi meters. And even every single snapshot of the wave has also a wavelength of 2 pi meters. This one has a wavelength of 2 pi meters. The red one has a wavelength of 2 pi meters. It goes down, it goes up, it goes down. So all different snapshots of the wave also need to have a wavelength of 2 pi meters, right? So the wavelength being equal to 2 pi over k is working out, okay? Let's change the values of the omega and the k just so we can see if it also works out. So what I'm going to do now is I'm going to try k is 2, omega is 1. Let's see what happens. Okay. K is 2, and then the units would be rads per meter. Omega is 1 rad per second, right? And then the phase angle, I'm still keeping it 0 rads. And then the amplitude is 1 meter. So what does this wave look like? So just to keep it simple, let's just erase this here and then do it right on the actual same graph. Draw our general equation. Y is going to be sine of 2x minus, and then since omega is 1, t, right? What is this wave going to look like at different snapshots? So let's choose t is 0. At t equals to 0, y is going to be sine of 2x. Well, what's going to happen? When x is 0, right, y is going to be sine of 0, which is just 0. So it's going to also start with the same phase angle. It's going to start at the origin. When x is equal to, I'm going to choose the same x, pi over 2, y is sine of 2 pi over 2, which means sine of pi, right? The 2's cancel, which means 0. So that means already the wave has gone up and gone down. So what's going to happen? When x is pi over 4, right? The wave will reach its maximum. Sine of 2 pi over 4 is going to be sine of pi over 2, which is 1. So what's happened? The wave has shrunk. You can already tell. So pi over 4 would be less than 1. So something like that. The wave goes up, goes back down, right? And basically the wave has shrunk by twice, right? And then when x is equal to pi, where y is equal to sine of 2 pi, is 0. So that means it's going to go like that. And then when it's 3 pi over 4, so this is pi over 4, and this is 3 pi over 4, the wave goes down, and then goes back up. And now you can actually fit 2 complete waves in a 2 pi meter distance, right? So you can go like that, one more, goes up, goes back down, then goes down, and then goes back up. So does this wavelength thing work out? Right? So 2 pi over k. The k that I have now is 2, right? The k that I'm trying is 2 rads per meter. Well, if you do 2 pi over 2, what are you going to get? You're going to get pi meters. Well, definitely that makes sense now. The wave has shrunk. And in a distance of pi meters, the wave goes up and down and goes back to where it started. So the wavelength is now pi meters, which is 3.14 meters. Okay? So that one works out. So now let's take different snapshots of the wave. Okay? So let's say at t equals to, just like we did before, we said at t equals to pi over 2 seconds. What's the wave look like? So now you have here y equals sine of 2x minus pi over 2, right? So what's going to happen? When x equals to 0, you're going to have y equals sine of negative pi over 2, which is negative 1. So let's do this in a different color. So this is negative 1 right here, right? When x equals to, we could do pi over 4 if you want. We could try pi over 4, and then we can try pi over 2. So when x equals to pi over 4, you're going to get what? Y equals sine of 2 times pi over 4. 2 2 times pi over 4 minus pi over 2, you're going to get what? Y equals sine of, this is 2 times pi over 4, that's going to be pi over 2 minus pi over 2. So that's sine of 0, which is 0. Right? So the wave at pi over 4, it goes like this. The wave is gone this, like that. Right? And if we don't have to do too many things. Once we do a couple snapshots, we can see here what's going to happen. When x equals to pi over 2, y equals to sine of 2 times pi over 2 minus pi over 2. And then you get y equals to sine of 2 times pi over 2 is pi minus pi over 2. That's pi over 2. And that's going to be 1. So then that's going to be over here. So the wave has gone over here. So its wavelength, of course, shouldn't change. We just want to see how far it has moved over. So then I can simply draw now. Then it's going to look like this. It's going to look like this. Like this. Like that. Goes back down. Goes back up. And so on. So how far has it moved over in that time interval? So you see, it's moving to the right. It's moving to the right. This point is moving there. This point is moving there. Every point of the wave is moving to the right, same distance. What's that distance? Right? Because you got to subtract here. Distance is pi over 2 minus pi over 4. And then it's pi over 4. Okay, because you got to get the same denominator, right? 2 pi minus pi, that's pi over 4. And then that's the distance. So the distance it has moved is actually less, right? It only moved pi over 4. It's moved less than the previous wave. So then, what should the velocity be? So all I needed really was 2 snapshots. I don't even need one more snapshot of the wave because I can kind of see a pattern here. So the velocity of the wave is going to equal the distance over the time. How much did it move over? Pi over 4 meters. Divided by how many seconds? Our snapshot was pi over 2 at 0 and at pi over 2 seconds, right? So we do pi over 2 seconds. And then the velocity would be what? 2 goes up there, and then you have 2 over 4, which is 1/2 meters per second. So this wave is shorter wavelength. We already saw that by twice, right? And it's moving slower. It's moving half as fast, 1/2 meter per second. Let's see if our general equation works. V is equal to omega over k, right? What was the omega we tried? 1 rad per second. And then you divide that by 2 rads per meter. Okay? And then rads cancel. You have 1/2 meter per second. So the general equation is working out. Omega over k works out. It gives you the right units, and it gives you 1/2 meter per second for the velocity, and this also gives you 1/2 meter per second for the velocity omega over k. So now we can say that's a generalization. Now what would happen if I reverse the sign of the wave? The 2x plus t. What would simply happen? The progression of the wave in different snapshots would move to the left, right? So we would say whenever you have negative, you have waves moving to the right. Whenever you have positive, the progression of the wave moves to the left, so it propagates to the left. Okay? So we can go back to our general equation of a wave. We can rewrite this way. We can factor out the k from here and then write x minus omega over kt plus phi, right? And since we established that omega over k gives you the velocity of the wave, we can write the general wave equation like this. A sine k x minus vt plus some phase angle. Okay? So this describes a transverse wave propagating to the right, and then this one would be transverse wave propagating to the left. Okay, in the next lecture, I'll talk about the direction of the wave and the velocity of the wave in the y direction, because we want to know what the perpendicular motion is doing. Okay, thank you very much.